Good morning. Thank you very much for that introduction. I'm John Sylak-Glassman, and this is Nicki Dlugash, and we build mapping software for Mapbox. And today we'll be talking about the challenges that cartographers face when trying to build a dynamic global map for a multilingual user community. Dynamic global maps are an increasingly common part of everyday life for anyone with an internet connection. You probably used a dynamic global map to find a nearby restaurant and then get directions to go there while you've been here in Montreal. And when we talk about dynamic maps, we mean maps where data is updated regularly, where the map display style can be changed, and where the view is slippy and changes in response to user input. Users expect these maps to cover the entire world, which means that they contain hundreds of millions of map features. So solutions to any problem with the map have to be done at scale, and manual editing, except at the highest levels, is usually not an option. And another challenge is that global maps require styles that look good in any location. So to serve a global multilingual user base, a significant focus of our work is generating and displaying a multilingual map, which we define as being a map that contains labels in a user's preferred language and the local language of the region being viewed. For example, a map like this, which shows the New York, New Jersey metro area with labels in both English and Mandarin Chinese. And as a side note, this map was made using the expressions feature of Mapbox GLJS that Molly Lloyd discussed yesterday during Practical Cartography Day. So we'll discuss three main components of building a multilingual map. One is generating multilingual data, and then using dynamic text rendering for multilingual labels and applying typographic styling correctly for multilingual maps. So to provide labels in a user's preferred language, we need to gather and transform map label data. And we do that through two main techniques, translation and transliteration. And these apply in different scenarios. So we use translation when the transformation between the name in a source language and the name in a target language is unpredictable. And we use transliteration when the transformation is predictable. In the latter case, the correspondence between sounds in the two languages makes it possible to predict roughly how a name will sound when transferring it from a source language to a target language. But this begs the question, how do we know how predictable the transformation will be? And the answer is simple, we don't. But we can make an educated guess based on linguistic principles. So more prominent names, like the names of countries, major cities, national capitals, are likely to have been in a target language for a longer time and to have been borrowed in an earlier stage from a source language. And so it's more likely that the transformation will involve an unpredictable element, either because the earlier stage of the language adapted names more drastically, or because it adapted them from a completely different source. So the case of the name Moscow, which is natively Moskva in Russian, is interesting. It could be either that we adapted it at an earlier stage in English that less predictably adapted the va element to ao, or it could be that we got it from German. And with Zhongguo, which is the approximate native name of China. I know I don't do tones very well. That means Middle Kingdom, but we adopted the name China from Portuguese, so it's unpredictable to know that the name is going to be China. By contrast, the names of less prominent locations are likely to only be lightly adapted to aid pronunciation. So for example, the name Tazewell, which is the name of a county in Illinois, is adapted into Russian as Tazwell. And we can see the regularity of this process when we look at a similar name like Roswell, where the well portion is adapted in the same way. And the regularity of these adaptations makes them suitable for automated transliteration, which we can do at scale. So let's talk a little bit more about how we approach doing transliteration. So transliteration often refers to a combination of two distinct processes. One is phonetic adaptation, which changes the pronunciation of a string, and the other is transliteration proper, which is actually converting something from one script to another, but in theory not changing the phonetic composition. We'll continue to use the term transliteration to mean the combination of these two processes, since in practical applications, these two are almost always going to be present. So in the process of transliteration, we need to discover the sound correspondences and formulate them as rules. And if formulating these sound correspondence rules is easy and we can do it to account for most of the names in the source language going to the target language, then we can use a simple string replacement system like regular expressions. But if the process is more difficult and it's harder to figure out what these rules are and to get them to cover all the cases you need them to cover, then we need a more powerful system that can actually learn these rules. So let's talk about a simple case first, which would be transliterating names in, I'm assuming, Mexican Spanish to Russian. So this is an easier case because Russian has all the sounds of Mexican Spanish, and both languages use alphabetic scripts. And so we can work out all the correspondences and write comprehensive rules manually. And that's been done in the past, actually. Not by us, but by other companies. And so now that you've seen an example of an easy case, let's take a look at a more complex example based on a project that we're currently working on and experimenting with, which is transliterating English to Mandarin Chinese. This is a more difficult task because neither language contains all the phonemes of the other, or all the sounds of the language. In addition, the syllable structure must be constrained much more drastically in Mandarin than in English. And the languages use very different scripts. English uses an alphabetic script, and Mandarin uses a script in which each character represents both a syllable and an associated component of meaning. So let's take a look at an example so that we can see how this works. So in transliterating an English place name like Bluffton into Mandarin Chinese, we can break it down into a three-step process where first we convert the English spelling to pronunciation, then we convert the pronunciation in English to the pronunciation in Mandarin. This is like phonological loanword adaptation. And then we convert the Mandarin pronunciation from pinyin to actually being in characters. So it's this last step that is actually the easiest because Mandarin has, at least Mandarin as spoken in the People's Republic of China, has an official subset of characters set forth by the Xinhua news agency for transcribing foreign names. And in this subset of characters, there's usually a one-to-one correspondence between characters and pinyin syllables. So if we take a look at a subset of this table, you can see that most of the time for a given syllable, there is consisting of a consonant and a vowel. There's usually one character that realizes that syllable. In some cases, there are two, but there are ways to reduce that complexity that I'm exploring. But the other two steps of the transliteration process are more complex, going from English spelling to pronunciation and going from English pronunciation to Mandarin pronunciation. For these kinds of tasks, native speakers, literate native speakers of English can often pronounce most of the names that they see written in a text. But if you ask them to write rules for how they do it and ask them to write enough rules to cover all the names that you might encounter, it would be a prohibitively difficult task. And similarly, if you asked bilingual speakers to write all the rules for converting a name from English pronunciation to Mandarin, they'd be hard-pressed to do so. And so for those kind of tasks, we need systems that are able to learn what those rules are rather than just apply rules to a given input. And so we're experimenting with machine learning techniques, specifically neural networks, which can be used to discover the rules for converting English to English pronunciation and converting that to a Mandarin pronunciation. So just for a very brief background on neural networks, they learn to mimic input-output correspondences, which are essentially the rules that convert from, say, English spelling to English pronunciation. And we train these networks on thousands of input-output pairs, so examples of Bluffton spelled as it is in English and then its IPA realization, an International Phonetic Alphabet for its pronunciation. And we train the network over thousands of iterations over that data called epochs. And each iteration or epoch adjusts a large number of weights to increase the likelihood of generating a correct output. So just to visualize this with a simple feed-forward neural network with one layer, we first convert the input string, which I've just used ABC, AB here to represent, to a numerical representation. And there are many ways to do that, but you can just simply use the index of the character in the alphabet to get a numerical value. And then that numerical value on each of those input nodes is multiplied by weights that along these edge connections. And I haven't shown the weights, but they are there in neural networks. And then each node in the hidden layer is a sum of those inputs times the weights along the connections with a nonlinear function applied to that sum. And then finally, we go through a similar process to output nodes, and usually the value of the output node can be mapped to a given symbol. And it's usually more complicated than this, but this is a basic visualization of how the information is converted into a numerical representation and flows to an output node from which you deduce a syllable, or a symbol, sorry. So for most language tasks, neural networks achieve better accuracy than any other machine learning technique, and that's why we're experimenting with state-of-the-art neural net models to learn to do these difficult prediction tasks. So once we've actually built a system that does this successfully and transliterates English names into Mandarin Chinese, we can improve on how we process hybrid names, which consist of a proper name portion and a common noun portion. For example, Henry's restaurant. There's the name Henry, and then there's the common noun restaurant. And we need to transliterate the proper name, but translate the common noun. And to sort of conclude my portion of this, building automated transliteration capabilities will allow us to deliver many more labels in users' preferred languages, and handling hybrid names correctly will allow us to help users better discover places using their preferred language.
Thanks, John. Okay, so we're going to move on now to dynamic text rendering. So once we've kind of gathered and generated all of this multilingual data, how do we display it on a map? And so just to go back to what John was saying earlier, what do we mean exactly by dynamic rendering? So Mapbox.gl is a vector mapping library that uses OpenGL to render graphics directly on the GPU of a client device. And so it's dynamic because it's so fast that you can continually update and re-render the map in real time. And so this is just an example. You can see it's similar technology to that used in a lot of video games. There's real-time camera movements and data updates and style updates. And so this is a particular type of rendering problem, actually. And so why is it hard to display multilingual labels on dynamic maps? Like lots of other applications support multilingual labels or multilingual text, and they've been doing it for years. And so one of the main reasons is that most applications actually use like the browser or the operating system to do the text rendering. The apps don't actually perform the rendering themselves, but in order to make our maps dynamic using OpenGL, we kind of have to bypass these softwares, and OpenGL doesn't do text rendering, so we kind of implement that part on our own. And so this is especially hard with dynamic type because rendering this requires a lot of recalculations, especially for something like a curved label. You're constantly recalculating the text layout. And we also have to build like everything twice because we have two GL renderers. So we have one for web and one for mobile. And these different platforms have different limitations and available tools in order to build them. But luckily, there are guidelines and standards and specifications on global language support to help guide us, and these have been really helpful for us in the process so far. Standards, specifications put out by the World Wide Web Consortium on web type specifications. The Unicode Consortium maintains the Unicode standard, which is the charting character coding system. They also release a bunch of useful text layout algorithms, and we also lean a lot on the OpenType font specification developed by Microsoft. Also, we're lucky that base map labels are very specifically formatted. And so we're just considering mostly a limited scope for text rendering. You can see we have short lines in text labels, just a few lines, limited vocabulary and syntax, a lot of proper nouns and common nouns, very limited punctuation. So this makes our life a little bit easier. And so I'm going to talk through a couple of those key considerations that we consider for text rendering. And just a quick note, so in talking about text layout, we usually distinguish between like an abstract representation of a character, which in this case is like a Unicode code point, and a visual representation, which is a glyph. So I'm going to talk about 4 elements of text layout. The first is the text directionality, which is the direction of text flow within a single line. The text orientation, which is the glyph orientation relative to the text direction. Text shaping, which converts like the Unicode code point to a glyph, and line breaking. So most languages in the world use scripts that write from left to right, but some write from right to left, including like Hebrew and Arabic. And so this is a little complicated because right-to-left scripts are actually bidirectional. They usually have embedded left-to-right text segments, like numerals, Latin characters. So like how does a text renderer know how to display the order of the glyphs? And so we're using an implementation of a Unicode algorithm that kind of takes in the logical order of like the order in which the characters should be read from first to last, and kind of takes that and reorders it to the visual order of the glyphs. And so that was sort of discussing horizontal scripts, either left to right or right to left. And so these are actually fairly easy to render dynamically because we simply rotate the whole text block as needed to follow a line. But some scripts can actually be written horizontally or vertically, like Chinese. So Chinese can be written left to right or top to bottom. And so it's pretty common for maps to display either of these 2 orientations depending on the angle of the line. And so you can see, is this video running? So you can kind of see that the orientation of the line automatically changes as the angle of this line changes. So a related topic to directionality and orientation is text shaping, which is the process of converting the Unicode code point to a glyph. And so for Latin, there's a one-to-one correspondence of code points to glyphs. Some scripts have more than one correspondence, like Arabic. So the character has different visual forms depending on the position in a word. And that's so that, like, because Arabic script is cursive and the characters need to join with each other. And so you can kind of see that depending on the position of the character in the word, it's going to have a different visual form. And so this is an example of complex text shaping called contextual shaping. And there's a bunch of other, like, complicated ways to, like, render text. And so we currently support contextual Arabic text shaping in Mapbox GL, and we're working on the other capabilities right now. So I'm going to skip over line breaking, but we use an interesting algorithm that's really simple and is the same across all languages, even though languages do have different line breaking specifications. So I'm going to skip ahead so I can talk a little bit about typography for multilingual maps. This is kind of like the last piece that kind of ties everything together, and I'm mostly going to be talking about font selection and type styling. And so we at Mapbox have in production English label map predominantly. And so the text styling here was mostly designed for English. And so I'm going to go over like a couple considerations in redesigning this map to better support multilingual maps. And so this is kind of tricky because we apply the same global styling rules to all languages. And so our goal is really like more to redesign the map from the ground up with consideration for all multiple languages, and so not just to adapt our English map. And so there's kind of like 4 general questions that we've been thinking about with typography. So whether the labels are visible, are they all equally legible, do they look harmonious together, and is there equivalent hierarchy and categorization across all labels? And so kind of the most basic concern is making sure the labels are actually visible on the map. So if you have all the language data in the world, it doesn't really matter if you don't use a font that can support all these languages. And that's actually like a little bit harder than it sounds because font files like can't actually contain all the information to support all languages. So in our renderers, we kind of handle this by declaring font stacks in a style. So we define a fallback system for font usage. So if a glyph is displayed in the first font in the stack that supports it. So you can see here, like Tartine script, the first font supports English but not Chinese. Arial Unicode supports Chinese. So that's kind of how we handle it. And so we use these font stacks listed here in our English map. So the first font supports Latin, Cyrillic, and Greek, and the second font supports the rest. But I just wanted to quickly mention, so another reason that it's like really hard to find fonts that support all languages is that it's a really hard task, and there's not really many use cases for like total, complete global language coverage. So mainly operating systems and browsers need this, and so not surprisingly, Google is the one who develops the most extensive font family for language support, and it's open source, and we're currently considering using it as a fallback. So I'm gonna quickly talk about like legibility across different languages, so mainly across different scripts. So just pointing out, there's a bunch of categories of scripts that need a larger minimum legible text size. Like Arabic is a very tall script, Chinese is a very dense, complex script, and so these need a little bit more text size and more line height to be legible. So if you like optimize for Latin, like a lot of languages appear to be too small on a map. And this is especially true if using bold weight, because it just makes the more complex glyphs even harder to read. And so you can kind of see here, just like an adapted version that's a little bit more comfortable to read. So I'm going to talk about labels looking harmonious together, which really means like, do the different languages like look and feel similar on your map? And so there's a bunch of different cases in the bilingual use case that we've defined where you'll see a bunch of different scripts in the same map display. So it's really important that they all look harmonious together. And this is like mostly about font selection in your font stack, I think. And so we try to match along some key characteristics. So like the general design and overall proportions and text weights of the fonts. And like all the fonts in, for example, a family like Noto will be harmonious together. And so you can kind of see a comparison of one of our font stacks. So DIN and Arial Unicode, they are both geometric sans serif, so they kind of have a similar look and feel, but Arial Unicode is definitely wider. It's got a higher X height, so it looks visibly larger at the same text size. And this is a little bit harder to compare when you're looking across scripts, but you can kind of do the same comparisons. So overall, this font stack is like okay for multilingual maps. It's not the best, I think. And then I think for time, I might skip over this last section, but really when we're talking about equivalent hierarchy and categorization across all labels, we are talking about equally supporting all languages on a map. So not really making English the priority. And so you can kind of see here, this is our English map styling applied to Chinese, and a lot of the hierarchy and categorization is kind of lost. And so here you can see comparison with, we actually do have a Chinese base map as well, and there's better hierarchy on this map. And so really the challenge is like combining all the optimal styling for all languages to make sort of a single style that works equally well across the different languages. So that's it. That's all we have for today. And so just to summarize, we've covered a bunch of different considerations for data, text rendering, and typography related to multilingual maps. And so we're really actively working on this stuff right now in order to display many of the world's languages on a map. And plus, we didn't get to talk about this, but we're working on a bunch of other challenges too, specifically along displaying a user-preferred language and a local language on a map together, including like customizable language fallbacks. And again, this is kind of like the result we're kind of looking for. So there's many moving pieces in order to create something like this, and we hope that by doing so, we'll better connect people across different regions and languages. And if you're working on similar projects, please come talk to us. We'd love to chat with you about these problems, and thank you.